Hey guys, tonight we embark on a profound journey into the deep future to witness the fate of the largest single feature on our planet. We will traverse hundreds of millions of years in a single night, following the inevitable path of tectonic destiny that will see the vast Pacific Ocean shrink, wither, and finally vanish forever. This is not a story of catastrophe, but of planetary rhythm, the slow, breathing pulse of Earth that closes oceans and forges new worlds from the fragments of the old. We will explore the mechanisms of this great closure, the forces that drive it, and the first whispers of the new supercontinent that will rise from the waves. So, before you settle in, if you're finding comfort in these deep time journeys, please consider liking this video and subscribing to the channel. We would also love to hear from you in the comments below. Tell us where you are listening from and what time it is there. It's always fascinating to connect with our global community of geography dreamers. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's epic journey together. You are not floating on the surface of the present-day Pacific. You are a sentient pulse of energy, a seismic whisper traveling through the cold, dense basalt of the Pacific Plate itself. You are sliding, inexorably, northwestward at the speed of a growing fingernail. Above you, the water column extends for miles, but your destiny lies below. You are approaching the abyssal plain of the Mariana Trench, the deepest point on Earth. The pressure around you is unimaginable, yet it is nothing compared to the fate that awaits. You reach the trench's inner slope and the world tilts. You are no longer moving horizontally. You are descending, beginning a plunge into the underworld. The rock around you groans with the strain of seduction, bending downward into the mantle. This is the Ring of Fire, not as a map feature, but as a living, consuming engine. You are witnessing the primary mechanism of the Pacific's destruction, the process that, minute by minute, century by century, is pulling this ocean basin back into the heart of the Earth. The story of the Pacific's closure is written in the fundamental rules of plate tectonics, and it begins with understanding its unique nature among Earth's oceans. The Atlantic Ocean is an adolescent, still widening as the Mid-Atlantic Ridge diligently forges new crust, pushing the Americas away from Europe and Africa. The Indian Ocean is a complex puzzle of spreading ridges and transforming boundaries. The Pacific, however, is ancient. It is the last remaining remnant of the Panthalassic Ocean, the vast global sea that surrounded the supercontinent Pangaea over 250 million years ago. Its fate is sealed by its geography. It is almost entirely encircled by subduction zones. These are the scars where oceanic plates, having cooled and grown dense over millions of years of travel from their mid-ocean ridge birthplaces, surrender to gravity and plunge back into the mantle. This destiny is not new. It has been underway since the Pacific Ocean first began to form. The entire history of this basin has been a balance between creation and destruction. Along the East Pacific Rise, a fast-spreading mid-ocean ridge, new basaltic crust is born in volcanic fury, pushing the plate westward. But this creation is outpaced by the consumption at its margins. The Ring of Fire is the visible manifestation of this destruction, a nearly continuous 40,000-kilometer-long chain of deep ocean trenches, volcanic arcs, and fault lines that frames the ocean basin. From the Tundra-Chromatic Trench in the southwest to the Peru-Chile Trench in the east, and from the Aleutian Trench in the north to the complex system of subduction zones around Southeast Asia, the Pacific is being actively and relentlessly recycled. The driving force behind this process is the powerful mechanism of slab pull. As the leading edge of an oceanic plate subducts, its descent into the hotter, less dense mantle creates a tremendous gravitational pull on the rest of the plate behind it. This is the most powerful force driving plate tectonics. Think of it as a tablecloth sliding off a table. Once the weighted edge begins to fall, it pulls the rest of the cloth with it. This is why the Pacific Plate is one of the fastest moving plates on Earth, traveling at up to 10 centimeters per year towards its fate in the trenches. This process is self-sustaining and incredibly efficient. It ensures that no oceanic crust, no matter how ancient, can survive forever. The oldest Pacific crust is already about 200 million years old, found in its western depths. As this crust is consumed, the ocean floor grows progressively younger towards the eastern spreading center. This continuous conveyor belt from ridge to trench is the heartbeat of the ocean, and its rhythm is gradually slowing the Pacific's vast heart. The evidence for this ongoing process is written across the entire Pacific Basin in a language of deep time. The Hawaiian Emperor's seamount chain serves as a visible record of the Pacific Plate's movement over a stationary hotspot, creating a trail of volcanoes that curve dramatically, marking a change in plate direction about 47 million years ago. The immense transform faults that offset the East Pacific rise testify to the complex stresses acting upon the plate. The deep ocean trenches themselves are the most dramatic evidence, with the Mariana Trench plunging to nearly 11,000 meters below sea level, creating the deepest natural point on Earth. These features are not static, they are active, dynamic components of a system in constant motion. The earthquakes that regularly shake the circum-Pacific region are the audible groans of this massive engine at work, each tremor a release of the incredible strain built up by the relentless convergence of plates. The volcanic eruptions that the Ring of Fire are the surface expressions of the melting that occurs as oceanic plates descend into the mantle, releasing water and other volatiles that lower the melting point of the overlying rock. This entire system operates with a terrifying beauty, a coordinated dance of destruction that has continued for tens of millions of years and will continue until the Pacific Ocean ceases to exist. How can we possibly know the fate of something as immense as the Pacific Ocean? The evidence is not found in a single crystal ball, but is pieced together from multiple lines of geological inquiry, creating a compelling forecast of continental drift. The first key to predicting the future lies in understanding the past. By studying the magnetic fingerprints locked in ancient rocks, the paleomagnetic record, geologists can reconstruct the precise motions of continents over hundreds of million years. These records show us the opening of the Atlantic, the northward journey of India, and the gradual closure of the ancient Tethys Ocean that once separated Gondwana from Laurasia. This history provides the pattern. Oceans that are surrounded by subduction zones close, while those with active spreading centers at their core open. We can then apply this pattern to the present-day configuration. Detailed satellite measurements from missions like GRACE and GOES map Earth's gravity field with exquisite detail, revealing the density variations that signify subducting slabs deep beneath the surface. These gravity anomalies show the cold, dense oceanic lithosphere sinking into the warmer, less dense mantle, tracing the paths of subduction zones thousands of kilometers below the surface. GPS networks stationed on continents and islands around the Pacific Rim measure their current velocities with millimeter precision. These data points are not static, they are arrows on a map, showing us the direction and speed of present-day motion. North America moves west-southwest at about 2 to 3 centimeters per year. South America moves west at a similar pace. Australia drives relentlessly northward at nearly 7 centimeters per year. Asia displays complex internal deformation as it resists the incoming pressure from the Pacific Plate. These motions are the opening lines of the next chapter in Earth's geological story. The most powerful tools for forecasting the deep future are sophisticated computer models that simulate the geodynamics of the entire Earth. These models incorporate data on plate motions, mantle convection currents, the geometry of plate boundaries, and the physical properties of rocks at immense pressures and temperatures. Scientists run these simulations millions of times, testing different parameters to see which configurations are most stable and likely over geological time. The results are not a single, certain prediction, but a range of highly probable scenarios. The most prominent model, known as Amasia, suggests the next supercontinent will form as the Americas continue their westward journey, eventually colliding with the already amalgamated Asia-Australia. The Pacific Ocean will close in the process, while the Atlantic may continue to widen for a time before eventually succumbing to new subduction zones of its own. Another model, Nova Pangaea, predicts a similar outcome through a slightly different kinematic pathway. All credible models, however, agree on the central premise: the Pacific Ocean is doomed by its current tectonic setting. Its closure is not a matter of if, but when and exactly how. The evidence for these future scenarios is not merely theoretical, it can be found in the geological record of past supercontinent cycles. The assembly and breakup of supercontinents like Rodinia, Pannotia, and Pangaea followed predictable patterns based on the distribution of subduction zones and the geometry of continental masses. The very rocks beneath our feet contain the story of oceans that no longer exist, of mountain ranges that have been worn down to nothing, of continents that have journeyed across the globe. By understanding these past cycles, we can extrapolate forward with reasonable confidence. The minerals in ancient mountain belts, the magnetic signatures in volcanic rocks, the distribution of fossil species across continents, all these pieces of evidence come together to form a coherent picture of how Earth's surface has evolved over billions of years. This long-term perspective allows us to see the Pacific Ocean not as a permanent feature, but as a temporary configuration in Earth's ever-changing geography, one that is currently in the process of gradual elimination through the relentless forces of plate tectonics. The grand, final closure is still over 200 million years in the future, but the opening acts of this tectonic drama are already playing out on stage today. We can see previews of the Pacific's fate in the ongoing collisions happening at its margins. These are the microcosms of the continental collisions to come. The most dramatic preview is occurring in the intricate archipelago of Southeast Asia. Here, the northward-moving Australian continent is already colliding with the volcanic island arcs of the Indonesian region. This is not a simple, head-on collision, but a complex, grinding interaction that is shattering the crust, uplifting mountains like those in New Guinea and Timor, and closing small ocean basins like the Banda Sea. This process, known as arc-continent collision, is the first step in welding disparate landmasses together. Similarly, the Philippine Sea Plate is being squeezed between the advancing Eurasian Plate and the powerful Pacific Plate. The islands of Japan and the Philippines are the volcanic expression of the subduction zones consuming the Pacific crust, but they are also being compressed and accreted onto the Asian margin. Each major earthquake in this region, each tremor that shifts the land by meters, is a small adjustment in this vast, slow-motion collision. Even the mighty Himalayas, though related to the closure of the Tethys Ocean, provide a perfect analog for the kind of continental collision that will eventually characterize the final closure of the Pacific. The impact of India into Asia shows us how continents behave under extreme compressional force. The crust thickens to double its normal size. Massive thrust fault stack slices of rock upon one another, and the Earth's crust wrinkles upward to form the highest peaks on the planet. Another critical process already underway is the migration and initiation of subduction zones. For an ocean to close completely, subduction must eventually occur on all its sides. We can see the early stages of this along the western margin of the Atlantic, where small, tentative subduction zones may be forming off the coasts of Puerto Rico, and the Lesser Antilles. While the Atlantic is currently opening, the future may see it develop its own ring of fire, sealing its own eventual fate. In the Pacific, the subduction zones are already mature and active. Their gradual inward migration will continue to eat away at the ocean's expanse, like a lake slowly draining from all sides. The first tangible sign of the Pacific's end will be the closure of its northern and southern gateways. The Bering Strait, which periodically connected Asia and North America during ice ages, will close permanently as tectonic convergence overcomes the shallow seafloor. The Drake Passage, the tempestuous stretch of water between South America and Antarctica, will also narrow and eventually close, reconnecting the Americas with the frozen continent and altering global ocean circulation forever. These initial closures will mark the point of no return. The biological implications of these early collisions are already becoming apparent. As land bridges form and disappear, species are able to migrate between previously isolated regions, leading to dramatic biotic exchanges. The Great American Interchange that occurred when the Isthmus of Panama formed 3 million years ago provides a small-scale preview of the biological revolutions that will accompany the larger-scale closures happening across the Pacific. As the Bering Strait closes, Asian and North American species will begin to mix on an unprecedented scale. Similarly, the collision between Australia and Southeast Asia is already allowing species to move between these previously separate biological realms. These biological exchanges will accelerate as the Pacific continues to close, eventually leading to a homogenization of the world's biota and the extinction of many species that are unable to compete in the new, connected world. The closure of the Pacific is thus not just a geological event, but a biological one as well, with profound implications for the future evolution of life on Earth. We would be fascinated to know where you're joining us from on this journey through deep time. As our story continues to unfold, feel free to share your location and the time there in the comments below. What has been the most striking image for you so far? The descent into the Mariana Trench, the computer models of Amasia, or the ongoing collisions in Indonesia? Let us know. Your engagement helps shape our community and our future stories. Now let the immense, patient forces of plate tectonics settle your mind. The slow grind of continents is the most permanent rhythm our planet knows. As the great machinery of subduction has been set in motion, and its consequences are now beginning to reshape the face of the Earth itself, we find ourselves in a world that is still recognizable, yet profoundly altered. The Pacific Ocean is still a dominant feature, but it is a king whose realm is steadily diminishing, whose power is slowly waning. This is the age of convergence, a time of colossal construction where the planet forges new mountains and new land masses from the fragments of the old. To those of you who are new to our channel and finding resonance in this geological epic, we extend a warm welcome. If these stories bring you peace and wonder, please consider liking this video and subscribing to join our community of deep time travelers. We are always curious to know where in the world you are listening from and what moment of the day or night you've chosen for this journey. Feel free to share thoughts in the comments. Hearing which aspects of the story capture your imagination most deeply helps us craft these narratives. Now, let the fans' hum blend with the whispers of shifting continents, and let us continue our descent into the narrative. Imagine a time-lapse map spanning 50 million years. The change is immediately visible. The Pacific Ocean no longer dominates the globe. Its vast blue expanse has noticeably contracted. The Americas have advanced significantly westward. The distance from California to Japan has been reduced by thousands of kilometers. The island chains of the Pacific, Hawaii, the Line Islands, the Emperor Seamounts, are no longer isolated specks in a great blue wilderness. They have been drawn inward toward the converging continents, like flotsam pulled toward a drain. Many of these volcanic islands, long extinct and cooled, have succumbed to erosion and subsidence, their peaks fading beneath the waves only to be scraped off and accreted onto the continental margins as the plates carrying them are subducted. The most dramatic new geography is emerging in the Pan-Asian region. Australia has completed its northern journey, colliding firmly and finally with Southeast Asia. The island arcs of Indonesia, the Philippines, and Japan have been completely crushed and sutured onto the Eurasian continent, forming a new, continuous coastline that is a complex tapestry of mountain ranges, peninsulas, and new inland seas. The Sea of Japan has closed. The South China Sea is a distant memory. The topography is fresh and jagged, a product of recent and ongoing tectonic compression. Great rift valleys form behind the new mountain ranges as the crust adjusts to the immense pressures. The Bering Strait is now the Bering Isthmus, a permanent land connection between North America and Asia that has created a continuous supercontinental landmass from Alaska to Sumatra. This new land bridge, far wider than the one that existed during Pleistocene ice ages, has already triggered a dramatic exchange of species between the Old World and the New. In the South, the story is equally dramatic. The Drake Passage between South America and Antarctica has narrowed to a shallow, narrow seaway. The powerful Antarctic Circumpolar Current, which once isolated the frozen continent and helped regulate global climate, has been choked off. Antarctica, still largely ice-covered, is beginning to feel the effects of its changing connections. Its northern peninsula is being dragged northward, and the first signs of tectonic uplift are visible along its Pacific margin. The world map is becoming simpler, cleaner. The complex fractal coastline of the modern Pacific Rim is being smoothed and straightened by the relentless process of convergence. The ocean itself is changing character. With a reduced surface area and different circulation patterns, its chemistry and biology are evolving. The stage is being set for the final act. The transformation of the ocean basin extends beyond mere shrinkage to fundamental changes in its very nature. The Pacific's famous Ring of Fire has intensified, with volcanic activity reaching unprecedented levels as the remaining oceanic crust is forced downward at an accelerating rate. The seafloor itself is changing, with the gradual subduction of the East Pacific rise altering the fundamental dynamics of the basin. The chemical composition of the ocean waters is shifting as hydrothermal activity increases along the diminishing mid-ocean ridge system. The sheer weight of the water mass decreasing has isostatic implications for the ocean floor itself, which begins to rise slightly in response to the reduced load. These changes create feedback loops that further accelerate the transformation process, demonstrating how interconnected Earth's systems truly are. The climatic consequences of this geographical rearrangement are nothing short of revolutionary. The Earth's climate system is fundamentally governed by the distribution of continents and oceans, which dictate ocean and atmospheric circulation patterns. The closure of the Pacific and the formation of new land connections is throwing this system into disarray, creating a planet that would be almost unrecognizable to us. The most immediate impact comes from the alteration of ocean currents. The great gyres of the Pacific, the North Pacific Current, the Kuroshio, the Humboldt, weaken and eventually break down as the ocean narrows and its basin shape changes. The equatorial counter-current stalls. The transfer of heat from the tropics to the poles is significantly disrupted. The closure of the Central American Seaway millions of years ago rerouted ocean currents and contributed to the formation of the Antarctic ice sheet. Now, the closure of the Pacific itself triggers changes orders of magnitude greater. The formation of the new supercontinent, which we might call Amasia or Nova Pangaea, creates a climatic regime dominated by extreme continentality. The interior of this massive landmass is so far from the moderating influence of the ocean that it experiences temperature swings of staggering severity. Summers are scorching hot, with temperatures soaring well above 50 degrees Celsius, 122 degrees Fahrenheit. Winters are brutally cold, with temperatures plummeting to -40 degrees Celsius, -40 degrees Fahrenheit or lower. Vast deserts, larger than any today, dominate the continental interior, their sands whipped by powerful winds that blow unimpeded for thousands of miles. The new mountain ranges that ring the supercontinent create immense rain shadows, blocking moisture from reaching the interior and further exacerbating the aridity. The carbon cycle, the great regulator of long-term climate, is also thrown into overdrive. The uplift of new mountain ranges, like the modern Himalayas, accelerates the weathering of silicate rocks. This chemical weathering draws carbon dioxide out of the atmosphere, acting as a cooling agent. However, this is counterbalanced by a massive increase in volcanic activity. The subduction of the final remnants of the Pacific crust, along with the eventual subduction of the mid-ocean ridge itself, triggers a period of unprecedented volcanism around the new supercontinent. Volcanoes pump enormous amounts of CO2 and other greenhouse gases back into the atmosphere. The climate of this future Earth oscillates wildly between greenhouse and icehouse states, a violent teeter-totter between volcanic fury and the silent, patient work of rock weathering. This climatic turbulence will last for millions of years, creating an environment of extreme stress and rapid change for the biosphere. The changes extend to precipitation patterns across the globe. The monsoon systems that currently affect Asia, Africa, and the Americas are completely reconfigured. Some regions that today receive abundant rainfall become deserts, while formerly arid areas might receive unprecedented precipitation. The distribution of tropical cyclones shifts dramatically as the warm pool of the Western Pacific contracts and eventually disappears. Sea ice formation around Antarctica increases initially as the circumpolar current weakens, but eventually decreases as the continent is drawn northward and its climate moderates. These changes are not isolated but interconnected, creating a cascade of effects that ripple through the entire climate system. The atmosphere itself may change in composition, not just in terms of greenhouse gases, but also in aerosol content from increased volcanic activity, potentially leading to more spectacular sunsets, but also affecting global temperatures through increased reflection of solar radiation. Life on Earth, which has always been shaped by the arrangement of continents and oceans, faces its greatest reorganization since the breakup of Pangaea. The biological world is entering a period of incredible upheaval, mass migration, and accelerated evolution. The formation of the Bering Isthmus and the closure of the Indonesian Seaway have created a continuous landmass that spans much of the northern hemisphere. This has eliminated the biogeographic realms we know today, the Palearctic, Nearctic, and Oriental, merging them into one vast superrealm. The Great American Biotic Interchange that occurred 3 million years ago with the formation of the Isthmus of Panama was a mere preview. This is the Great World Interchange. Species are on the move. North American fauna spreads into Asia, while Asian species reverse migration into the Americas. Competition is fierce. Generalists and highly adaptable species thrive in the new, connected world. Specialists, particularly those endemic to islands or isolated ecosystems, face extinction as they are outcompete or fall prey to new predators and diseases. The unique marsupial fauna of Australia, already pressured by earlier connections to Asia, is now completely overwhelmed by an influx of placental mammals from the north. The flightless birds of New Zealand, which evolved in the absence of terrestrial mammals, are wiped out by newly arrived predators. This is a time of great biological homogenization, a tragic loss of unique biodiversity built up over millions of years of isolation. In the oceans, the story is equally dramatic. The shrinking Pacific is losing its deep-water habitats. The unique ecosystems of the hydrothermal vents and hadal trenches are the first to go, destroyed as the seafloor is subducted. Marine species with wide distribution survive, but those endemic to the central Pacific perish. The closure of the Drake Passage and the changes to global thermohaline circulation alter nutrient upwelling patterns across the planet. Some current marine hotspots become biological deserts, while formerly barren areas blossom with life. The altered ocean chemistry, a result of changed circulation and volcanic inputs, forces another great reset for marine life. Extinction events ripple through the food web, followed by rapid radiations of new species adapted to the changed conditions. Life is resilient, but it is being fundamentally reshaped by the closing of the Pacific, forced down evolutionary paths that will define the biosphere for the next 100 million years. The biological changes extend to the microscopic world as well. Changes in ocean chemistry and circulation patterns alter the distribution of phytoplankton, the base of the marine food web. On land, soil ecosystems are transformed as continents collide and climate zones shift. The distribution of pathogens and diseases changes as species come into contact for the first time, leading to new epidemiological challenges for surviving populations. The very air that organisms breathe changes composition as the balance between photosynthesis and respiration shifts with the changing distribution of ecosystems. These microbial and chemical changes may ultimately prove more significant than the more visible transformations in larger organisms, as they affect the fundamental biochemical cycles that sustain all life on Earth. The closure of the Pacific is thus not just a geographical event, but a biological one that will echo through the evolutionary history of our planet for hundreds of millions of years to come. As our story continues to unfold, we again extend an invitation to our global audience. Your presence in this community is what gives these stories life beyond the script. Where are you tuning in from tonight? What has captivated you most in this vision of a world remade? The shifting geography, the climate chaos, or the biological revolution? Share your thoughts with us. We read every comment and are continually inspired by your engagement. Now, let the scale of these changes, the migration of continents, the transformation of climates, the evolution of life, lull you into a deeper state of relaxation. The story is vast, but your place in it as a witness is unique. Carry this perspective with you as we move toward the final stages of the Pacific's great story. We arrive now at the final act of our story, the last 100 million years of the Pacific Ocean's existence. The changes we have witnessed so far accelerate, culminating in the ultimate geological event, the complete closure of an ocean basin and the birth of a new supercontinent. The world we enter now is alien, a testament to the endless creativity of tectonic forces. The Pacific is but a shadow of its former self, a shrinking inland sea surrounded by the towering peaks of the greatest mountain range ever to exist on planet Earth. This is the epoch of final convergence, the last great collision. To our longtime listeners and those who have just joined us on this incredible journey, we thank you for sharing this exploration of deep time. If this narrative has offered you a sense of perspective and wonder, please help others find it by liking and subscribing. We are always deeply moved to see the comments from around the world, from night shift workers in Jakarta to early risers in Reykjavik. Tell us your favorite part of the saga. Does the fate of the oceans or the resilience of life speak to you most profoundly? Now, Let the final movements of this planetary symphony begin. Settle in, breathe deeply, and let's witness the end of an ocean. The point of no return arrives not with a cataclysm, but with a geological technicality, the subduction of the East Pacific Rise. For over 200 million years, this mid-ocean ridge has been the engine of the Pacific Plate, the divergent boundary where new crust is born and pushed outward. But now, the westward advance of the Americas has brought the continent to the ridge's very doorstep. The spreading center, unable to resist the relentless push of mantle convection from below and continental resistance from above, begins to bend. Finally, it reaches the Peru-Chile Trench. The subduction of an active mid-ocean ridge is one of the most geologically significant events possible. It represents the death of a tectonic plate. As the ridge is forced down into the trench, the source of new Pacific crust is literally cut off. The conveyor belt stops. What remains of the Pacific Ocean is now a finite quantity of crust, and the process of its destruction accelerates dramatically. The powerful force of ridge push, the elevated mid-ocean ridge sliding down due to gravity, vanishes overnight in geological terms. Only slab pull remains, and with no new crust being created, the entire system contracts rapidly. The world is now dominated by the new supercontinent, which we will call Amasia, as it is the most widely accepted model for this configuration. Amasia is a sprawling, misshapen landmass that incorporates almost all of Earth's continental crust. The Americas have collided with Asia, welding together along a suture zone that runs from modern-day Kamchatka to Alaska and down through the already amalgamated Bering Isthmus. The collision is not clean. It is a complex, multi-stage process that creates a mountain range of mind-boggling proportions. This is not a single chain like the Himalayas, but a vast, wide zone of deformation, a Himalayan-scale event stretching for thousands of kilometers. The forces of compression are so great that the crust thickens to over 70 kilometers in places. The topography is a chaotic jumble of towering peaks, high plateaus, and deep, intermontane basins. The subduction of the East Pacific Rise triggers a period of incredible volcanic activity unlike anything witnessed since the Earth's earliest history. As the spreading center descends into the mantle, it carries with it vast quantities of water and other volatiles that dramatically lower the melting point of the surrounding rock. This leads to massive melting events that produce enormous volumes of magma, which erupt at the surface in catastrophic volcanic events. These are not the relatively gentle eruptions of shield volcanoes like Hawaii, but explosive, caldera-forming supereruptions that dwarf anything in human history. The ash and gases released into the atmosphere would have profound effects on climate, potentially triggering rapid cooling events that would further stress the already transforming biosphere. This volcanic crescendo represents the death throes of the Pacific Plate, a final fiery protest against its inevitable consumption. The final stage of the Pacific's life is not as an open ocean, but as a great inland sea, much like the Mediterranean Sea today, but on a far grander scale. This terminal body of water, which we might call the Panthalassan Sea or the Final Pacific, is surrounded on all sides by the high mountains of Amasia. Its connections to any remaining global ocean are tenuous at best, perhaps through a narrow strait in the south. This sea is deep, holding the last of the ancient Panthalassa crust, but it is shrinking fast. Its shorelines are transient, retreating year by year, century by century, as the subduction zones on its periphery continue their consumption. The climate of Amasia is extreme beyond anything previously experienced on Earth. The supercontinent's interior is a hyperarid desert, a vast barren wasteland of sand and rock where temperature variations between day and night can exceed 60 degrees Celsius. Rain is a rare event, and what little falls often evaporates before reaching the ground. Life in the interior is limited to extremophiles, organisms that can withstand incredible desiccation and temperature swings. The mountain ranges that ring the interior create a perpetual rain shadow, wringing every drop of moisture from the air before it can reach the heart of the continent. These mountain ranges themselves are biological islands, hosting unique ecosystems isolated from one another by the deadly deserts below. Along the coasts of the shrinking inland sea, conditions are more moderate but still harsh. The sea itself acts as a limited climate moderator for its immediate shores. Volcanic activity is rampant around its perimeter, a last gasp of the subduction process that is consuming the final pieces of oceanic crust. These volcanoes pump ash and gases into the atmosphere, further complicating the climate patterns. The final chapter of the Pacific Ocean is written in this inland sea. Its waters grow ever more saline as evaporation outstrips input from rivers and precipitation. Eventually, it may come to resemble a giant dead sea before finally drying out completely. The last vestiges of marine life in this sea undergo a brutal evolutionary bottleneck, adapting to extreme salinity and fluctuating water levels until the final day when the last pool of water evaporates, leaving behind a vast, salt-encrusted basin, the final grave of the Pacific Ocean. The mountain ranges that surround this dying sea are unlike anything existing on Earth today. They represent the cumulative compression of thousands of kilometers of former ocean basin, stacked and uplifted to create peaks that likely exceed the height of Mount Everest by significant margins. The geology of these mountains is incredibly complex, with rocks from the deepest ocean trenches now found at the highest elevations. The erosion of these mountains would be phenomenal, with landslides of unimaginable scale periodically reshaping the landscape. Rivers flowing from these heights would carry incredible sediment loads to the lowlands, gradually filling what remains of the ocean basin. The very weight of these mountains depresses the crust beneath them, creating a feedback loop that further elevates the peaks while deepening the surrounding basins. This is a landscape of superlatives, the most extreme topography our planet has produced in hundreds of millions of years. The closure of the Pacific Ocean is complete. Where once the greatest ocean on Earth rolled its waves, there is now only land, the high, dry, salt-encrusted floor of a vanished sea, surrounded by the highest mountains the world has ever known. The event will be recorded in the rocks with perfect clarity for any future geologists to read. The evidence will be everywhere. Ophiolites, slices of oceanic crust, and upper mantle thrust up onto the continents, will be preserved along the entire suture zone between the Americas and Asia. These spectacular rock sequences will preserve pillow basalts, sheeted dikes, and mantle peridotite, telling the story of the ocean's birth at a mid-ocean ridge and its death in a subduction zone. The incredible mountain range that marks the collision will be riddled with evidence of the ocean's former existence. Marine fossils will be found high in the mountains just as we find Tethyan fossils in the Himalayas today. The limestones that formed in warm, shallow seas will be thrust to breathtaking altitudes. The patterns of magnetic anomalies on the seafloor will be lost to subduction, but their story will be preserved in the accreted terrains, the fragments of island arcs and oceanic plateaus that were scraped off the subducting plate and plastered onto the continents. The death of the Pacific gives birth to a new geological world, one that will be studied and puzzled over for eons to come. But this is not the end of the story. It is merely the completion of one chapter in Earth's endless supercontinent cycle. The formation of Amasia creates a new geological reality. The concentration of most continental crust into one landmass will have profound effects on mantle convection. Heat will build up beneath the supercontinent, eventually causing it to dome upward and weaken. Rifts will begin to form, perhaps within 100 million years of Amasia's assembly. These rifts will widen into new ocean basins, and the cycle will begin again. The fragments of Amasia will be carried away from each other on the backs of new tectonic plates, traveling across the globe to eventually collide once more in a new configuration hundreds of millions of years in the future. The Pacific is gone, but the process that consumed it will eventually give birth to new oceans, ensuring that the face of our planet remains forever dynamic, forever changing. The legacy of the Pacific extends beyond the geological into the biological realm. The great biotic exchange that accompanied its closure will have permanent effects on the evolutionary trajectory of life on Earth. New species will evolve to fill the niches created by the new supercontinents' extreme environments. The genetic mixing that occurred as previously isolated populations came into contact will provide raw material for evolutionary innovation for millions of years to come. The extinction events that accompanied the ocean's closure will clear the way for new forms of life to emerge. In this sense, the death of the Pacific Ocean is not an end but a transformation, a necessary step in the ongoing evolution of our planet and its biosphere. The patterns of life that emerge from this period of upheaval will define Earth's biology for the next supercontinent cycle until the process begins again and yet another ocean closes to make way for new worlds. Now, as we bring our story to a close, let your mind rest on the incredible patience and power of our planet. The Pacific Ocean, which seems to us a permanent fixture of our world, is but a temporary feature in the deep time of Earth's history. Its story of birth, expansion, and eventual closure is a powerful reminder of the transience of all things and the beautiful, relentless cycles that govern our world. May this perspective grant you a profound sense of peace. The world changes, but it endures. Let the certainty of these great cycles ease you into a deep and restful sleep. Thank you for journeying with us. Sleep well and good night. you.